Okay, so first thing that we always do with a physics problem is go ahead and draw out what's happening. So we got a little table here. There's my table. Got a block on the table. There it is, and it's attached to a spring. Now where is the spring attached? It says the spring is currently stretched out along the table surface. So that means, I guess, the spring is stretched out this way. It's attached to something back here. I don't know what it is, but something back there. And it said it is stretched 3 centimeters beyond where it wants to be. So that is the 3 centimeters of the stretch. We're drawing it in. What else do we know? We know the mass is 0.5 kilograms. We know the spring constant, that is symbolized with K, that is equal to 200 newtons over meters. And the first question we're asked is, how much work does this spring do on the block as it returns it to equilibrium? Okay, so here's the block. And it's returning to equilibrium, so I guess that means it's moving 3 centimeters back towards its happy location here. And the spring force is going to be aiding that. The spring force is wanting to go back to its equilibrium position. All right, so for part A, we want to know about work done by the spring force. So fortunately, we just derived an equation for that. It is -1/2 the spring constant. And we have the final position squared, and we subtract the initial position squared. So let's see, we got K, there it is. The final position, we're moving it back to equilibrium. So that means my final position is 0. And my initial position, well, that is 3 centimeters off this way. And it actually doesn't matter if that's negative or positive because it's squared, so I'm not even going to worry about that. That's my initial position. And then I guess K is 200 Newton meters, and we see, problem, newtons and meters and centimeters here, so let's switch this over to meters. There are 100 centimeters per meter. So this is going to be, I wrote it terribly, but that is going to be 0.03 meters, and double check, fewer meters, more centimeters. So yeah, 100 centimeters in a meter. So that makes sense. That's our initial position. So we just go ahead and plug in 200 Newton meters for the spring constant, 0 for the final position, 0.03 meters squared for the initial position. Go ahead and plug that into our calculator. Well, I guess we don't actually even need to do that. 200 divided by 2 is 100 Newton meters, so those two go into that. 0 squared is still 0. This guy squared, 0.03, is 0.0009. Meters squared is meter squared. And then we multiply this by 100, so the decimal place moves over 2, and we get 0.09 newtons over meters times meters squared. Oh no, I have lost some negative signs. Let's go back and correct those. There was a negative sign here, so there needs to be a negative sign there. So there needs to be a negative sign here. So there needs to be a negative sign here, except there's also a negative sign here. So those two match, and this is positive. So I made 2 mistakes, and they cancel each other out. Not a good idea to depend on that, but it worked this time. So meters and meters, there we go, those cancel. And for the work done, we get positive 0.09 newtons times meters, and newtons times meters are joules. So 0.09 joules. Okay, should the work be positive? The displacement is this way and the force is the same direction. It should be positive. Okay, so that's good. So that's the answer to A. What's the net work done? All right, so now we're asking not about a work done by a specific force, but the work done by all forces. So here we should take your book's advice and draw a free body diagram. So we got the spring force acting that way. It's on the table, so I guess there's going to be a normal force from the table, and it's near Earth, presumably. Tables are pretty much, as far as I know, only showing up on Earth, so there's going to be gravity. And those are all the forces, and because we're doing work, we should also put the displacement on here. So there's the displacement. And now looking at this, we can say, oh, that guy does no work because the normal force points up and the displacement is perpendicular to each other. Force is perpendicular. So that is the little symbol for perpendicular to displacement. And when that happens, there's no work done. And that's also going to be true of gravity. So in this case, the net work, the sum of all the work, which would normally be the work done by gravity, plus the work done by the normal force, plus the work done by the spring. Well, that one's 0, and that one's 0. So all we have is the work done by the spring, which we solved for down here. So the net work on this guy is 0.09 joules. So that's B. Next, C. What is the change in the block's kinetic energy? So here we should go back to your book again, and it says when you're doing an energy and work problem, use the work energy theorem. And I guess more correctly, this isn't just kinetic energy, this is the change in energy. But all we've got here that's changing is kinetic energy. So the sum of all the work acting on an object is equal to the change in the object's energy, and in particular here, it's equal to the change in the object's kinetic energy. And that's what we're asked about. What's the change in the object's kinetic energy? Well, it's equal to the net work by the work energy theorem. And we have already solved for the net work. It is equal to 0.09 joules. All right. Cruising right on. D. Here we're told that the block is initially traveling 0.2 meters per second away from the equilibrium length of the spring. So the force of the spring is this way, but it's going that way. That's its initial velocity. And it wants to know how fast is it going when it gets back to equilibrium. So that means we know the amount of work it does, 0.09 joules. That's the net work. And that is all equal to the change in kinetic energy. And so we'll write in, that's going to be 1/2 times mv squared. That's the final kinetic energy minus 1/2 mv initial squared. That's the initial kinetic energy. And we're told the initial velocity. And we know the mass, it's up here. And we know the net work, so I guess we can go ahead and solve this equation. But let's do it before we plug in the numbers. Let's do it with the symbols. So we are trying to solve for the final kinetic energy. So we will add the initial kinetic energy term on both sides. So we'll end up with the net work plus 1/2 the mass times the initial speed squared. That equals 1/2 the mass times the final speed squared. And we're solving for this, so let's multiply both sides of the equation by 2. So we can cancel the 1/2. And then let's divide by the mass. So we can cancel this mass. And then we've got the final speed squared. And that is going to be 2 times the work, the net work. I'm going to multiply to distribute, this 2 times the net work. And then 2 over here times this kinetic energy term. The 2 and the 1/2 will cancel. So we'll be left with the mass over the initial velocity squared, and all of that is over the mass. And we'll move a little bit more, have a little extra paper here. So then now we could split this fraction up. 2 times the net work divided by the mass plus the mass times the initial velocity squared over the mass. So just split up the fraction into 2 separate fractions. That's equal to the final velocity squared. And this mass cancels, but that mass doesn't because there's no mass here. So gotta be careful. It's very tempting to just cancel these masses here, but you can't do that because there's no mass in this term. So we get 2 times the net work over mass plus the initial velocity squared. And we're going to take the square root of both sides because what we want in the end is the final velocity. And now we can go ahead and plug in for these quantities. And I guess I didn't do this very well, but we'll go now this way. All right, so 2 times the net work, that was 0.9 joules, over the mass is 0.5 kilograms, plus the initial velocity, that is 0.2 meters per second. All of that is squared. We take the square root. That'll give us the final velocity. And let's see, 0.2 times, let's see, that is going to be, if I plug it into my calculator, the numbers here will be 0.36 and the units. All right, so joules, those are equal to Newton meters. We're dividing joules by kilograms. Newtons are equal to kilograms meters over seconds squared times meters. All of that's over kilograms. So the kilograms will cancel. Meters times meters. Those will be meters squared. Seconds squared, those will stay second squared. Okay, so this is 0.36 meters squared over second squared plus 2.2 squared, that is 0.04 meters. Got to square the units too. Seconds, got to square them as well. Take the square root, and this is good. We got meter squared over second squared plus meter squared over second squared. Same types of units, we can add those. So we will get 0.40 meters squared per second squared when we add those two. Take the square root. And then the square of 0.4 is 0.6, bunch of stuff, but whatever. We're going to stick with 1 sig fig here. Meters squared, square root of that is meters over second squared. Take the square root of that, it's seconds. So here our final velocity is this, except for I misspoke. And I also wrote off the end of the page. I misspoke. It's not the final velocity. This is the final speed, because when you take the square root, of course, it could be the positive or the negative sign. We don't know which it is, but when we look back at the problem, we can tell. We pulled this block away from its equilibrium position, and then we gave it a speed going that way. But if it gets back to the equilibrium position, it'll go out, and then it has to travel back. So we actually know that this speed is going to be in that direction. So even though we just got the speed from the math, it could have been in either direction. We can use what we know about the situation to actually get the velocity. It's this magnitude and it's in that direction. And that is how you can solve a spring type problem with the work energy theorem.